Hello everyone. So today we are going to discuss about digital transformation of the analog filters. So in the previous video lecture, I have shown you the how to obtain the transfer function for the nth order Butterworth low pass filter. Okay. So let me share my screen to start off with. Okay. So now we are going to talk about the design procedure for a low pass digital Butterworth filter. So one thing which you have to understand here is that we have designed h of s, which is a system function for analog filter. So in this case, it's a low pass analog Butterworth filter. So now how can I get digital Butterworth filter, which is h of z rather, h of z. So now we are going to follow some process such that we can convert h of s into h of z. Okay, so let's assume that the digital low pass specification is given. So again, it's AP or AS, whether you are in a dB scale, A or epsilon, or A if you are in analog scale. Omega P and omega S are given. So this is discrete omega P and discrete omega S. So these are the digital low pass filter specification. If it is analog, then you will have a continuous omega P and continuous omega S. So understand the difference between the two. Okay. So following steps are to be performed for designing a low pass digital Butterworth filter. So true transformation are available such that we can obtain continuous omega p and continuous omega s from discrete omega p and discrete omega s respectively. The first one is an impulse invariance method where continuous omega p is equal to discrete omega p divided by t. Similarly, continuous omega s is equal to discrete omega s divided by t, where t is your sampling interval, which is nothing but 1 over sampling frequency. Bilinear, second one is the bilinear transformation. Continuous omega p is equal to 2 by t tan of discrete omega p by 2. And for continuous omega s, which is a stop band h frequency, this is 2 by t tan of discrete omega s by 2. So given discrete omega p, discrete omega s, I need to convert to continuous omega p and continuous omega s. Either I can apply impulse invariance method or bilinear transformation. But the gain or the attenuation, meaning that AP or AS, epsilon on or A of the analog filter is the same as that of the digital filter. So the y-axis value, whatever is the specification, would not change. The only thing is that discrete omega would be converted into a continuous omega with the help of bilinear transformation or impulse invariance. Once you have continuous omega p and omega s, AP, AS or epsilon or A, then I can compute the filter order, which we have done it before. So if it's a linear scale, you use this filter order expression. If it is a dB scale, you use this filter order expression for low pass Butterworth filter. Then you compute your omega c, which we have discussed about it in the linear scale. This is omega c in the dB scale. So make sure that you match omega p specification. Once you have n and omega c, then you can design a system function ha of s. Then you need to convert ha of s to h of z either through a bilinear transformation or impulse invariance method. So if in the step 1, if you have used impulse invariance method, then at the last step use an impulse invariance method. Last step meaning that step 5. If you have used a bilinear transformation at this in the step 1, then you have to use a bilinear transformation at step 5. So just make sure that you match the same approach. Okay. Now, bilinear transformation says h of z is equal to h of s, you replace s by 2 by t, 1 minus z inverse divided by 1 plus z inverse. That's a very simple way. Uh, Simple manipulation, substituting s by this specific expression, where t again is the sampling interval. Impulse invariance method is, in this case, h of z is equal to h of s, where s is going to be 1 over t ln z. So, or z is equal to e to the power of st. Okay, so this is how you have to apply bilinear transformation and impulse invariance transformation approach. One thing you have to understand here is, in the impulse invariance method there is a natural log term, ln term is there. So all the time in the in your h of z you cannot have a natural log term. So that's why I have given you a specific set of impulse invariance method, where if the form of h of s is a divided by s plus b, where a and p are some numbers, then your impulse invariance method h of z would be a divided by 1 minus e to the power of minus pt z inverse. So these are the sum of the general expression of h of s and the corresponding h of z from the impulse invariance. Okay, I'll go it in a little bit of more depth when I talk about impulse invariance method separately. Okay, this is, since we are talking about the filter design perspective, both from an analog as well as from a digital perspective. So this is how you can actually use this table to actually come up with a respective h of z from h of s from using an impulse invariance method. Okay, all right. So now let's take an example, because now we want to design a filter. Okay, design an IIR. So this is a probably for some of you guys might be a first time. IIR is an infinite impulse response. Obviously, it will have poles and zeros. Okay, so denominator component. So it will have definitely poles. It may or may not have zeros. Okay, so poles, obviously, Butterworth filter, what we have discussed so far is obviously the poles are located on a circle. So design an IIR low pass Butterworth filter using a bilinear transformation for the following specification. So the passband region is given this h of e to the power of j omega, magnitude is point, it's between zero point 0.8 to 1, where mod of omega is less than or equal to 0.2 pi. This is the passband region. And the stop band region, it's saying that the magnitude response should be less than or equal to zero point 0.2, and from where mod of omega greater than or equal to zero point 0.6 pi to less than or equal to pi. So, and assume t is equal to 1. So what all I need to design first here is, this is a discrete omega p is given and discrete omega s is given. Okay, so now I need to get the corresponding continuous omega p, continuous omega s. Once I get that, then then what do I do? So how do I convert first that using a bilinear transformation which is given. Okay, and then once I get that omega p and omega s continuous aspect, continuous version, then I can design, compute the filter order n, because I know that it's in a linear scale, and then I can get my omega c, I can get my omega h of s. Once I get my h of s, then I can apply a bilinear transformation approach to get h of z. So that's the process. Okay, so this is a general expression. Magnitude should be less than or equal to 1 divided by square root of 1 plus epsilon square and 1. This is mod of p is less than or equal to mod of omega should be less than or equal to omega p, and then this is the magnitude response. This is less than or equal to 1 over a. Mod of omega should be greater than or equal to omega s and should be less than equal to pi. So first thing is that you should know that since it's a um, the frequency component is limited from minus pi to pi, because the periodicity is 2 pi, because we are talking about DTFT, because this is a DTFT expression. Okay, so this is my pass band region, this is my stop band region. Now what do I do? 1 divided by square root of 1 plus epsilon square is 0.8 given in the question. So epsilon is going to be 0.75. Then 1 over a is equal to 0.2. A is going to be 5. Then omega p, continuous omega p is given as 0.2 pi. So sorry, discrete omega p is given as 0.2 pi. So the continuous omega p is 2 by t tan of discrete omega p divided by 2. This is going to be 2 tan of 0.2 pi divided by 2. So this is 0.65 radians per second. So omega p is given as 0.2 pi. So I'm going to put that. Similarly, for discrete omega s, the expression is, the value is 0.6 pi. So the continuous omega s would be same thing, would be the same thing. So continuous omega s is 2 tan of 0.6 pi divided by 2. This is 2.75 radians per seconds. Now, once I get the respective continuous omega p and continuous omega s, I need to compute the filter order. So this formula, we have seen it before. It's a linear scale. Apply the values. You are going to get 1.3011. So as I said before, the filter order would be the next higher integer value. So in this case, it's going to be 3. Sorry, it's going to be 2. Then you compute your omega c is equal to omega p epsilon squared to the power of 1 over 2n. So substitute the value, you are going to get 0.7506 radians per second. So this is the maximum computation which is required in terms of computing the filter order and omega c. So now in this case, it's a linear scale. So I apply the linear scale formula. Okay, if the expression was given in a dB scale, then I would apply a dB scale formula. Now for n is equal to 2, we already know that h of s is given by this expression, omega c square divided by s square plus square root of 2 omega c s plus omega c square. So I just substitute the value of omega c, and finally I get this answer. Now from here I need to design a h of z using a bilinear transformation. So h of z is equal to h of ha of s, where s is 2 by t 1 minus z inverse divided by 1 plus z inverse. Remember that t is 1 in this case. Okay, so wherever you see s in this expression, replace by this specific expression. So the finally, it's some sort of simplification which you have to do. Wherever you see s, replaced by this, because t is 1. So we simplify it, and finally we get this answer. So I hope the step which we have taken is pretty straightforward to you. So one thing is that discrete represent values, discrete frequency values are given. You need to convert into the respective continuous frequencies, and then you have to do the same thing what you have uh, done for designing an h of s for an analog filter. Once you get that, and then later on you convert into h of z. Okay, now I'm going to take a same example, but instead of a bilinear transformation, I'm going to use a impulse invariance method. So the question number 2 is design an IIR low pass Butterworth filter using an impulse invariance method with the following specification. Specification is the same, but the only difference here is it's an impulse invariance approach. As before, assume t is 1, as before a is 5 and epsilon is 0.75. Discrete omega p is 0.2 pi. So impulse invariance method says that continuous omega p is equal to discrete omega p by t. Since t is 1, so both of them will be equal. So continuous omega p is 0.2 pi radians per second. Similarly, discrete omega s was 0.6 pi, which is going to be the same thing as continuous omega s. Now I'm going to apply the same formula to compute the filter order. Okay, so once you put in the values of epsilon a, omega p, and omega s, then I'm going to get 1.7083. Again, the filter order here is n is equal to 2. So again, I'm going to use omega c is equal to omega p divided by epsilon squared to the power of 1 over 2n. So omega p is nothing but 0.2 pi, and then this is 0.75 to the power of half. Okay, and then I'm going to get this value. Now this is the filter. H of s is takes this form. Wherever I see omega c, substitute by 0.7255. Finally you are going to get this answer. Now Now I need to apply an impulse invariance method. So if you look at the table which we have discussed, which I have shown, so I want to make sure that my h of s falls in this particular region. Okay, so what I do and then the corresponding h of z is given. So what I do here is, I'll go back. So I will simplify this term in the form of this is 1.0216.513 divided by s plus 0.513 whole square plus 0.513 square. This is of the form b divided by a plus s plus a whole square plus b square. This is the h of z, corresponding h of z. So what I'm going to do here is a and b in this example happen to be 0.513 with the multiplicative term is this. So I put the multiplicative term and then wherever I see a, here I replace by 0.513 and b also the same value, and then finally I get this expression. So this is e to the power of minus 0.513 t is 1 sine of 0.513 z inverse divided by the numerator. This is the numerator, and then similarly the same thing you have to do for the denominator. Finally you get this answer. Okay, so your h of z is gonna be this expression. So what we have done is that we have designed a transfer function h of z for a given specification, either through a bilinear transformation and impulse invariance method. Now, for the rest of the lecture, what I'm going to do here is I'm going to talk about the Chebyshev low pass filter. Well, Chebyshev has two variant. One is type 1 and type 2. Okay, so I'm going to only talk about the type Chebyshev type 1, or simply we say Chebyshev low pass filter. Okay, and uh, so that's what we are going to talk about. But more importantly, why there is another analog filter design, which in this case is a Chebyshev. So there are some important limitations associated with the Butterworth filter. Okay, so that is why we want to do that. But in order to design a Chebyshev filter, that also have a pros and cons attached to it. Okay, a more rapid roll-off rate near the cutoff frequency, meaning that if there is a cutoff frequency which is at magnitude response of 1 over square root of 2, this cutoff frequency, so this more rapid roll-off rate than that of the Butterworth can be achieved at the expense of monotonicity in the pass band and or in the stop band region. So this roll off rate near the cutoff, or this slope near the cutoff frequency, if you want to make it more sharper, then one thing is that you keep on increasing the filter order for the Butterworth filter, but the issue with the Butterworth filter is it has to have with the all poles are there. Okay, so then so now, and that would increase the number of filter order, number of computation. So is there a way I can get a more sharper roll off rate with a lower filter order? Answer is yes, but you have to sacrifice the monotonicity either in the pass band or in the stop band or in both. So if you lose the monotonicity in the pass band, so meaning that in the pass band region you have ripples, okay, and then it's a monotonically decreasing function in the stop band, then we call it as a Chebyshev type 1 filter. Now, if you have a monotonically decreasing function in the pass band, but you have a ripples in the stop band, then it is called as a Chebyshev type 2 filter. There is another filter which is called as an elliptical filter, where the roll-off rate would be a lot faster compared to the other filters near the cutoff frequency, wherein you can have ripples both in the pass band as well as in the stop band region. So as I said before, I'm going to talk only about the type 1 Chebyshev filter. So there, what happens is that you have a ripples in the pass band region, and it's a monotonically decreasing the stop band region. When you sacrifice the monotonicity, then you get a lower filter order n compared to the Butterworth with the same specification. So as I said, we're going to talk about Chebyshev type 1 low pass filter, and it contains only poles. Okay. So again, we are going to talk about the square magnitude response. The squared magnitude response of an nth order Chebyshev low pass filter is given by this expression: h of j omega magnitude square is equal to 1 divided by 1 plus epsilon square Tn square omega divided by omega c. Epsilon is a passband ripple parameter. So how much of, it's not a monotonically decreasing function. Now you will have a slight ripple. Okay. And Tn within the bracket is called as it's a polynomial function, which is an nth order excuse me nth order polynomial function. How is this nth order polynomial function defined? Tn of x is takes the expression of cos of n inverse cosine of x for mod of x less than or equal to 1. What is my x here? X is nothing but omega divided by omega c. So this is omega divided by omega c. That means that mod of omega is less than or equal to mod of omega c. So that is going to be my passband region. Okay. Similarly, for mod of x greater than 1, that means that mod of omega greater than mod of omega c, which is nothing but a stop band region, I will have a function which is a hyperbolic cosine of n inverse hyperbolic cosine of x. Okay, so hyperbolic cosine of x is given by e to the power of x plus e to the power of minus x by 2. So that means that this cos function at the passband region will make sure that it gives you a ripple, and the hyperbolic cosine function in the stop band region, it will make sure that it is a monotonically decreasing function. Okay. Now, equiripple response in Chebyshev is due to the polynomial, which I think we have got already an idea associated with it. Now, what I'm going to do here is I'm just going to substitute, just to get a more intuitive idea about this nth order polynomial. I'm going to just substitute the values of n. Okay, so when n is 0, which is a very hypothetical situation where n cannot be 0, but this is a Chebyshev polynomial is a recursive polynomial, so that's why I need to know what happens at n is equal to 0. If n is equal to 0, this is 0, this is 0, cos of 0 is 1, and hyperbolic cos of 0 is also 1. Then what happens when n is equal to 1? When n is equal to 1, this is nothing but x. Here also it is x. So x, which is omega divided by omega c. Now Tn of 1. What is Tn of 1? Tn of 1. Tn of 1. So cosine inverse of 1 is nothing but it's going to be 0. So cos of 0 is 1. So here also inverse hyperbolic cosine of 1 is going to be 0. So hyperbolic cosine of 0 is going to be 1. So this is another one, Tn of 1. So when omega, so that means that Tn of 1. So wherever you see x, if this is 1, then the Chebyshev polynomial will take a value of 1. Okay, all right. So what this means is at omega equal to omega c, the Chebyshev polynomial is going to take a value of 1. Okay, right, 1. Now mod of x less than or equal to 1, mod of, since it's a cosine function, it will fluctuate between -1 to 1. Mod of x greater than 1, because it's a hyperbolic cosine function, Tn of x monotonically increases to infinity. Chebyshev polynomial is a recursive polynomial. So Tn of x is equal to 2x t n minus 1 of x minus of t of n minus 2 of x for n greater than or equal to 2. So if I want to get n is equal to 2 here, then I need to get 1 and 0. So that's why we need to get the initial values. And then it is a recursive. Okay. So now let's Get back to our square magnitude response for nth order Chebyshev low pass filter. So h of j omega magnitude square is given by 1 divided by 1 plus epsilon square Tn square omega divided by omega c, where x is obviously is omega divided by omega c. Now, at x is equal to 0, at x, when x is equal to 0, that means that omega equal to 0. At omega equal to 0, what happens to this term? Tn of 0. What happens to Tn of 0? If I go to this, so 0. So cos inverse of 0. Cos inverse of 0 is nothing but pi by 2. Pi by 2. So this is going to be n pi by 2. So depending upon the value of the filter n, if the n is odd, so if n is odd, so cos of n pi by 2, if n is odd, then it's going to be 0. If n is even, then it will fluctuate between plus or minus 1. Okay. So we, why I am not looking at an inverse hyperbolic cosine function is because I am looking at a passband region which is given by cos function here. Okay. So at omega equal to 0, continuous omega equal to 0, so I am going to get a value of 1 when n is odd. When n is even, I'm going to get a value of 1 over 1 plus epsilon square, because this is Tn 0, which is going to be square. So plus or minus will be 1. So 1 over 1 plus epsilon square when n is even. Similarly, when n is odd, it's going to be 1. So this is a very important concept. At omega equal to 0, you have to be magnitude square response for omega equal to 0, the filter order, if it is a filter order is odd, then it's going to be 1. If it is even, then at omega equal to 0, the magnitude square is going to be 1 divided by 1 plus epsilon square. So the where the ripple starts is, so the ripple for odd will start from 1, like this. But for even, the ripple will start from 1 divided by 1 plus epsilon square if you are looking at a magnitude square. If you are looking at just magnitude, then it will be 1 divided by square root of 1 plus epsilon square. Now, at x is equal to 1, meaning that at omega equal to omega c, then the magnitude square response is 1 over 1 plus epsilon square. This we have already discussed. So that's why in Chebyshev what we do is that omega c is equal to omega p. Okay. Now when x is between 0 and 1, so in other words the omega is between 0 and omega c, square magnitude response fluctuates between 1 and 1 between 1 and 1 divided by 1 plus epsilon square. When x is greater than 1, when x is greater than 1, omega greater than omega c, which is nothing but my stop band region, the square magnitude responses decreases monotonically to 0 because of the hyperbolic cosine function. At omega is equal to omega c, we do not have any constraint. So what we do is that we say that this magnitude square is nothing but 1 over a square. This is a very important conceptual difference between when the filter order is odd, when the filter order is even. When the filter order is odd, so first thing is that we are looking at a magnitude square response as a function of omega, and here also the magnitude square response. When filter order is odd, then the ripple starts at 1. When the filter order is even, the ripple starts at 1 over 1 plus epsilon square. You still have the ripples within this region. Okay, and then it's a monotonically decreasing function. And at this point, it should be the value afterwards in the stop band region, the value should be 1 over a square, less than or equal to 1 over a square. The same thing applies here. Now, sometimes what we do is that we do not put a square here, magnitude response. If that is a magnitude response, so make sure that you put a square root here and you make this as 1 over a. So the rest other things does not change. Okay. I hope this is clear. I hope this is clear to you. So now, what I'm going to do here is I'm going to talk about how to compute the system function for the Chebyshev nth order low pass filter. Okay, all right. And then, if the time permits, then we are going to see if we can go through one of the example associated with the Chebyshev. Okay. See, so in Chebyshev, I'm not going to go through much of the derivation associated with it, just to make sure the students to understand and the flow involved in computing the system function h of s. Okay, so this is the magnitude square response of nth order Chebyshev filter. So as before, what we have done for Butterworth, so we can break it down into h of s, h of minus s. Again, a I'm not talking about, that is understood, and s is equal to j omega. Okay, so wherever you see omega here, you put s by j. Now, location of poles can be determined by equating the denominator to 0. So 1 plus epsilon square Tn square S divided by j omega c is equal to 0. So without going into the math, in terms of the derivation aspect, I'm going to just write down the formulas associated with it. To ensure causal and a stable H of S, the poles Pk equal to sigma k plus j continuous omega k should be on the left hand side of the S plane. This is the formula for sigma of k, and this is the formula for a continuous omega of k. So this is minus continuous omega c sine of pi divided by 2n 2k plus 1 hyperbolic sine of a. So similarly, it's the same term with a cosine and cosine hyperbolic cosine of a. What is a? A is nothing but 1 over n inverse hyperbolic sine of 1 over epsilon. Okay. So now, what we do here is that these are actual location of the pole for, so in this case k goes from 0 1 so on to n minus 1. So we have already taken care of the poles on the left hand side of the S plane, so that's why we are written k is equal to 0 1 2 so on to n minus 1. If the filter order is, say for example, 3, you will put k is equal to 0 1 and 2. Similarly, you are going to get p naught 1 p1 p2. Okay, that's it, and then the corresponding these values. Okay, but still the complex conjugate pair will still be valid. If there is a complex pole, then you will have a complex conjugate pair. Now let's do a simple math here. I'll take this sigma k and I'll take this guy, put it at the denominator. No, no, sorry. I'll take this sigma k, this one, and this one at the denominator and make it square, plus this one and divided by continuous omega c cosine hyperbolic cosine of a whole square is equal to, this is nothing but sine square theta plus cos square theta, that is going to be 1. So this is the equation of an eclipse which you are aware of. Okay, which is nothing but x over a whole square plus y over b whole square is equal to 1. So instead of poles being located on a circle, here the poles are located on a on an eclipse. Okay, so the shape, so sigma j omega, so the height here in the x-axis, this range is going to be omega c hyperbolic sine of a. Here this will be omega c hyperbolic cosine of a. Now, to get a system function, we have to take the poles on the left hand side, which is going to be s minus pk, the product on the poles on the left hand side, and numerator term has a k, has a constant parameter. This is a normalizing factor such that we make sure that at omega equal to 0, if the filter order is 1, then the magnitude response, no, sorry, I'll take it back. Let me rephrase. K is a normalizing factor such that at omega equal to 0, at the magnitude response for a filter order odd, the value would be 1. If it is filter order is even, it makes sure so the value is 1 divided by square root of 1 plus epsilon square. Okay, so this is how you have to compute, right? So now, as before, we'll go to determination of filter parameters n and omega c of a Chebyshev low pass filter. As you can rightly see here, in this expression, I need to know what is my n and what is my omega c. But by this point, you should have an idea that omega c is equal to omega p in a Chebyshev. Okay, so my design specification can be in a linear scale. So if it is a linear scale, so again, this is 1 over 1 plus epsilon square, magnitude square. This should be between this value and 1 in a pass band region. In a stop band region, the value should be less than or equal to 1 over a square. So omega c is equal to omega p. So this is the best part of Chebyshev, where you do not have to compute the value of omega c as opposed to in the Butterworth filter. Okay, and now filter order n is given by this expression, inverse hyperbolic cosine within bracket square root of a square minus 1 divided by epsilon divided by inverse hyperbolic cosine of omega s divided by omega p. If it is a linear scale, so expression I'm not going to go through again because we have seen this before in Butterworth, omega c is equal to omega p. So n is equal to given by this filter order expression. And then epsilon is given by square root of 10 to the power of ap divided by 10 minus 1. So now let me go through one specific example just to give you a idea about how to compute the Chebyshev system function h of s. Okay, so because for filter design related problem, it is always better to make sure that you solve it by yourself, because once you solve it, you will have a better idea of what you are actually doing. Okay, so this is the question. I'll just give this question for a second for you to read. Okay. Design a Chebyshev analog filter with a maximum passband attenuation of 2.5 dB at omega p is equal to 20 radians per second. So your AP is going to be 2.5 dB. A minimum stop band attenuation of 30 dB at omega s is equal to 50 radians per second. So your omega s is 50 and your AS is going to be 30. Since it's an analog filter, I have to design h of s. So how we go about doing that? So first thing what we see here is this is a dB scale. So I have a formula for the dB scale. This is the dB scale formula. So I go back and look at put that this is n is equal to inverse hyperbolic cosine of the numerator as well as the inverse hyperbolic cosine of the denominator. So I substitute the values carefully, and then my filter order is going to be n is 2.72. So my filter order is 3. My omega c is going to be 20 radians per second because that is equal to omega p. Now you think about this. So the poles are located on an ellipse, okay? And now you have a 3 poles are should be there. So one, so on the left hand side, if I go back here, this one, 3 meaning that one pole will be here, P naught, P naught, P1 and P2. Okay, so P naught and P2 should be a complex conjugate pair, and the P1 would be on the real axis. If say for example the filter order is 4, then you will have P naught, P1, P2, P3. So P naught and P3 will be complex conjugate pair, and then P1 and P2 will be a complex conjugate pair. So I hope you got that idea. Okay. So n is equal to 3. n is equal to 3, so that means that I need to have one value on the real axis, the another should be a complex conjugate pair. So let me see whether I get that. So epsilon is given by square root of 10 to the power of AP divided by 10 minus 1. So I just substitute the values, I get 0.8822, and then I get the value of A. It's given in the formula. So the formula associated with the Chebyshev is little denser than the formula involved in Butterworth. Okay, so you compute the value of A, which is 1 over n inverse hyperbolic sine of 1 over epsilon. So this is 1 over 3 epsilon value, this is 0.3242. Then what you do is that this is the formula for the sigma k and continuous omega k. So this is the formula which we have. K goes from 0, 1, and 2. And so hyperbolic sine of A and hyperbolic cosine of A we can compute because it is required here. So when you put k is equal to 0 here, so sigma naught and continuous omega naught expression you can compute. So this is minus 3.3 and 18.2385. Similarly, k is equal to 1, so because this is going to be 0 for k is equal to 1 because it's on the real axis. So sigma 1 is minus 6.6, sigma 2 will be minus 3.3, and then continuous omega 2 here would be the minus because it's a complex conjugate pair. Okay, so your P naught would be minus 3.3 plus J 18.2385. P1 would be minus 6.6. P2 is going to be minus 3.3 minus J 18.2385, which is nothing but P naught conjugate. So your H of S is K divided by S minus P naught, S minus P1, S minus P naught conjugate. P1, P1 is 6.6 minus 6.6. So this is S plus 6.6. And then S minus P naught and S minus P naught conjugate will give you this S square plus 6.6x S plus 343.53. Now, what is the value of k? So this is a odd function, odd filter order. So odd filter order, if you go back, so you want to make sure that at omega equal to 0, the value should be 1. Okay, then you compute the value of k. So what we do here is S is equal to j omega. So at S is equal to 0 also you can put at S is equal to 0. This is k divided by 6.6 multiplied by this term. The value should be 1. So this is k is going to be this. So finally this is going to be your answer. H of S is equal to 2267.3 divided by S plus 6.6 S squared plus 6.6 S plus 343.53. That's it. So this is how you have to do H of S. Now, how do I design a digital transformation of Chebyshev filter? So how we do that is, again, we have to apply impulse invariance and bilinear transformation. So this is again a design procedure. It's exactly the same thing, but the only thing is that you have to make sure that you compute your H of S from the Chebyshev perspective. So I'm not going to go through it again here, this one. So omega p to continuous omega p, omega s to continuous omega s, you know that you can apply impulse invariance method or bilinear transformation. So the gain or the attenuation of the analog filter is the same thing of the digital filter. Then you compute the filter order if it's a linear scale, if it is a dB scale. Remember, in both the cases omega c is equal to omega p. Then you compute a value, and then you compute the location of the poles given by the formula. Then you compute your H of S, and then use the transformation chosen in the step 1 and transform H of S to H of Z. So that this is exactly what we want to do. Okay. So just what I will do here is I'll talk about one more example, and then I think that will give us of how to design an analog filter for a Butterworth and a Chebyshev filter, Butterworth and a Chebyshev filter, and then digital filter for Butterworth and a Chebyshev filter for low pass filter specification. We are just talking about the low pass filter here. Okay. So let me go through this example. Determine the system function h of z for the Chebyshev digital low pass filter that meets the following specification: 1 dB ripple in the pass band region. So this is your AP value, which is going to be 1 dB. Your omega p is going to be 0.3 pi. At least 60 dB attenuation. So that means that your omega s is 60 dB in the stop band. For you make sure that this is mod here, mod of omega less than or equal to 0.55 pi, and less than, sorry, greater than or equal to 0.55 pi mod of omega, but less than or equal to pi. Okay, so this is your omega s is given by this. Okay, and assume t is equal to 1. First thing is that you close your eyes and apply a bilinear transformation to get the continuous omega p and continuous omega s. So you substitute the value, finally you are going to get this answer. Then it's a dB scale. So you know the formula for the dB scale to compute the filter order, and you substitute the values. Okay. Now in this case, the filter order is too high. This is 5.615. So the filter filter order you are going to select is 6. So means that you have one in a let me go back to that pole zero schematic. Excuse me. So it is 6, meaning that 3 here and 3 here. Okay. So omega c is equal to omega p. So that is given as 1.0191. You compute the value of epsilon, you compute the value of A. Then you compute the location of poles through the formulas which are given. So I'm not going to actual computation now. This is the answer: P naught, P1, P2. Now the corresponding is P3 should be P2 conjugate, P4 should be P1 conjugate, P5 should be P naught conjugate. Then finally, h of s is equal to k divided by s minus p naught and its conjugate, s minus p1 and its conjugate, s minus p2 and its conjugate. So you fill in the values and expand it. So you get a rather three separate quadratic expression. Then finally the k is there. So now you need to determine the k. K is even. So means that you put s is equal to 0. So k divided by this value multiplied by this value multiplied by this is equal to 1 over square root of 1 plus epsilon square. Okay, what is epsilon square, which is computed, is 0.5088. So you compute that, you are going to get the k value as that. So your final answer is going to be this. So since it's a bilinear transformation, so h of z is equal to h of s would be s is equal to 2 by d 1 minus z inverse divided by 1 plus z inverse. Okay, so this is how you need to design a digital Chebyshev low pass filter. Yes, we do agree that the math involved with the Chebyshev filter design is a little bit more tedious, and a lot of expressions are there compared to the Butterworth. So make sure that you understand those things carefully. Now, before I stop this lecture, let me give you a difference between the Butterworth and a Chebyshev low pass filter. Butterworth low pass filter magnitude responses, as we know that it decreases monotonically with increase in frequency from 0 to infinity. Chebyshev low pass filter, obviously you have a ripples in the pass band region, but it's a monotonically decreasing function in the stop band region. The width of the transition band. So transition band is the region between omega p and omega s, both continuous. Okay. So the width of the transition band is more for a Butterworth than the Chebyshev. I mean, in other words, the slope of the transition band is lot shallower in Butterworth than in the Chebyshev filters. Poles are located on a circle for Butterworth, while the poles are located on a eclipse. Okay. The number of poles in the Butterworth filter is more compared to that of a Chebyshev filter of the same specification. You can have the same specification, and if you want to design a Butterworth and a Chebyshev, the number of poles required, or the number of poles, in other words, the filter order, which in turn relates to the filter order, would be lower compared to the Butterworth. So the order is higher for Butterworth, which involves the more number of computational complexity. Practical implementation, what we do here is that we use Chebyshev as filter as the number of computational complexity is reduced. Okay, so these are some basic differences between the Chebyshev and the Butterworth low pass filter. So I hope the lecture here helped you to understand how to design Chebyshev low pass filter both in the analog as well as in the digital domain as well. Okay, all right. So let me stop at this point. Okay, thank you very much.